Okay, so let's dive in. We're looking today at solving right-angled triangles, which is actually pretty powerful stuff.
It really is. And the source material we've got, well, it gives a pretty solid introduction, walks through some examples too.
Yeah, finding those unknown sides and angles, and our goal really is to pull out the core idea from this source.
Which is basically how, if you know just a couple of things about a right triangle, like say a side and an angle, or maybe two sides, you can figure out, well, everything else about it.
Using trigonometry, right, those key relationships, it feels really efficient, like getting a lot from a little.
Exactly. Maximum information from minimum input. That's a good way to put it.
So the source breaks it down. It mentions two main situations you run into.
That's right. Two main scenarios. The first one is where you know one side and you also know one of the acute angles. Not the right angle, obviously, one of the others.
Okay, side and an angle. Got it. And the second?
The second is when you know two of the sides, but maybe none of the acute angles yet.
Right. And what's interesting, the source shows these aren't totally separate problems, are they? They use the same toolkit.
Pretty much. It all comes down to those fundamental tools, the trigonometric ratios, sine, cosine, and tangent.
Through the link, yeah.
Yeah.
Between the angles and how the side lengths relate to each other, the proportions.
Precisely. They bridge that gap between angles and sides. It's all built on those specific pairings, opposite, adjacent, hypotenuse, relative to a certain angle.
So the source makes it clear. Figure out what you want to know, an unknown side, and what you do know, a known side. Then look at the angle you have and pick the trig ratio that connects those two specific sides.
Exactly. Is it opposite and hypotenuse? That's in spherical. Adjacent and hypotenuse. Cosine. Or maybe opposite and adjacent.
Tangent. And the source mentions cotangent too, right? Which is adjacent over opposite.
Yeah, sometimes the reciprocal functions like cotangent are useful too. It just depends on what sides you have and what you need.
Okay, and the source has examples for that first case side and angle given. How does that work, generally?
Well, the general approach shown is setting up a simple equation. You basically make a fraction, the unknown side over the known side, and you set that equal to whatever trig ratio matches those sides for the angle you know.
Ah, okay, so like in one example, they needed side AB, which was adjacent.
Right, and they knew side BC, the opposite side, and also angle A.
So adjacent over opposite.
Yeah.
This cotangent of angle A.
Exactly. So the equation becomes ABBC equal called cot angle A. You pop in the number for BC, look up the value for cotangent of angle A, like cot 30 degrees is the square root of 3.
And then it's just algebra to find AB.
Yeah.
Simple.
Yep. Solve for the unknown.
Okay, so that covers finding sides if you have an angle. What about the other way around? You've got two sides, but you need to find an angle.
Right. Good question. That's where you need the inverse trig functions, arcsine, arcsine, arctangent.
The undo functions.
Sort of, yeah. The source shows you first calculate the ratio of the two sides you know. Let's say the opposite side is 5 and the hypotenuse is 10.
Okay, so the ratio is 5 over 10, which is 12.
Right. And since sine is opposite over hypotenuse, you're basically asking which angle has a sine value of 12.
And that's where you use inverse sine, like sinel.
Exactly.
Yeah.
You feed it the ratio, 12, and it tells you the angle. The source points out if you recognize that sine 30 degrees is 12, boom, you know the angle's 30 degrees.
Or another example they had, I think, was opposite and adjacent sides being equal.
Yeah, like 10 over 10, which is 1. Since tangent is opposite over adjacent, you need the angle whose tangent is 1.
Inverse tangent of 1, that's 45 degrees, because tan 45 is 1.
You got it. It's using the side ratio to work backwards to the angle.
So basically, these ratios and their inverses are the keys to the kingdom, whether you start with sides or angles.
That's the core message. And the source shows this isn't just for, plain simple triangles on a page.
Right, it applies them to more complex stuff.
Correct, like finding heights or diagonals in a rhombus or breaking down more complicated shapes, even mapping like a rocket's flight path.
How does that work? You just find the right triangles hidden inside.
Pretty much. You identify a right triangle within the bigger picture, solve for a side or angle using these methods, and then, critically, that answer becomes a known piece of information you can use for the next right triangle in the problem.
Ah, like a chain reaction. Solving one part helps you solve the next.
Exactly that. It's an iterative process. The source examples really highlight that strategy of connecting knowns to unknowns step by step using the ratios.
It really drives home how fundamental these simple triangle relationships are for geometry and just measuring things in general.
Absolutely. The source material really hammers home how these principles let you figure out Distances, heights, all sorts of dimensions and all kinds of shapes, and even real-world situations.
Just by finding those right triangles and applying sine, cosine, or tangent.
That's the essence of it.
So wrapping up this deep dive, guided by our source material, it seems like problems that look complicated at first glance.
Yeah.
They often just break down into a series of these solvable right triangles, if you know where to look.
That's a great takeaway. It's about seeing the simpler shapes within the complex ones.
So think about this. How often are these simple relationships where knowing just a couple of pieces lets you find everything else in a right triangle, the absolute foundation for calculating things we rely on?
Right, like architectural blueprints or navigation for ships and planes, land surveying, even tracking that rocket we mentioned. It seems incredibly complex, but
It all starts with a right angle, a couple of known values, and a ratio.
makes you think, doesn't it? How much we can figure out from so little.